name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on exam technique for the OCR June 2013 Unit 5 or F325 past paper. Now the whole point of these videos is to go through the past paper and write the answers down for them, but crucially to also go through and give you some little hints and tips as to how you can improve your exam technique. Whereas you might have a mark scheme for a past paper, this video aims to not only obviously go through the answers required for the mark scheme, but also explain why it might be the answer and give a little bit of understanding as to why that is the case. And this is obviously not normally found in the mark scheme, so it'd be quite useful to understand your answers as well. It is important to understand about exam technique. It's one thing knowing the content in the book, but it's a completely different skill to actually be able to answer an exam paper correctly. So this video is designed to go through all that. Also, it might be a good idea if you can try and get a hold of this past paper yourself. You can find them freely on the OCR website, and you can download them, have a go at them, and then answer the questions, and then check back on this video to see if you've got the answers right, and crucially to find out why it's right or why you didn't get it right. Also, if you see on the left hand side, there are some links to the different questions, so you can just skip straight to the question that you want to answer, so you don't have to go through the whole video. Okay, so let's make a start. So it starts off by looking at a standard definition, and in this case it's asking us about Born-Haber cycles. So it says Born-Haber cycles can be used to determine lattice enthalpies of ionic compounds. Define in words the term lattice enthalpy. So you can see we've got 2 marks here, so it's a standard one, so we need to write it's the formation of 1 mole of an ionic compound from its gaseous ions. Now, this is a thing you really just have to remember. You do get 2 marks. You get 1 mark. You must include the word 1 mole, and you must include these words, gaseous ions. So it's the formation of 1 mole of ionic compound from its gaseous ions. You must include them terms. They are actually marking points. So you get 1 mark for that and 1 mark for that. So there you go. There's your 2 marks for that. Okay. So obviously, if it's talking about Born-Haber, you would need to do a cycle as well. So they've thrown in a cycle for good measure. So it says the Born-Haber cycle below can be used to determine the lattice enthalpy of calcium oxide. The cycle includes the values for the enthalpy changes of the steps labelled A to G. Complete the Born-Haber cycle by adding the species present on the 2 dotted lines and include state symbols. So this question is for 2 marks, as you can see just at the bottom there. There you go. So it says 2 marks. So all we have to do is just complete these boxes here. Now you can see here that we've got this box here where we've got calcium plus O gas plus an electron. This one here, because calcium is in group 2, we have to ionize it to get to Ca2+. So this is actually the second ionization stage. So what we have to do is put Ca2+. All these ions, these are in the gaseous state, as per the definition. And there's the gas, oxygen gas, plus 2 electrons. So all we've done is we've effectively removed another electron from the calcium atom. The oxygen remains the same, and there's the extra electron there. And then this one is actually electron affinity. This is the second electron affinity. So we've got the first electron added onto the oxygen there, but we need to form O2-, so we need to add this electron to that oxygen. So we just need to write an equation to show that. So this is going to be Ca2+. And again, include your state symbols. These are always in the gaseous phase for this. Plus O2-, and again, gaseous phase. And there you go. So that is we've added this electron onto that oxygen there. So this is 2 marks. So obviously we just get 1 mark for each. So we get 1 mark for that. Give that a tick. And then 1 mark for that. And give that a tick. There you go. 2 marks. Easy. Okay. So on to the next question. Okay, so it says name the enthalpy changes for the following steps in the Born-Haber cycle. So we're looking at step A. So if I bring this cycle back again, and you can see there's step A there. So this one is actually we're going from the elements in their standard states and we're forming our compound. So that definition is going to be the formation of calcium oxide. So that's your first one there. Put that out of the way. Okay, so step A is formation of calcium oxide. Go. Okay, and then if we look at step C, bring that back in. So step C is this one. So you can see we're going from calcium gas and half O2 gas to calcium gas, but to O gas. So what's changed here is actually we've gone from molecular oxygen to just atomic oxygen. So we call this atomization of oxygen. Now you have to be specific in this question, and you have to say atomization of oxygen. We're going to put that there. So you must include both terms, atomization of oxygen. You can't just put atomization. So it's being specific. Okay, and then the next one is step G. So step G, if we look at our step here, is going from Ca2 plus O minus plus an electron to, and you can see the change here is going from O minus to O2 minus. So this is electron affinity, but this is the second electron affinity because we've done the first electron affinity here, adding the electron to the O minus, to the oxygen to form O minus, and now this is the second one here. So again, we have to specify which type of electron affinity this is, and this is the second electron affinity. And again, affinity means to kind of be attracted to it. So, and again, we're just going to put of oxygen, being specific. So with all of these, again, the key thing with the exam technique is to be specific as you can. That doesn't mean you have to add lots of waffle, but it's just being specific with what you're referring to. So you get 1 mark for each of them, so that's 3 marks in total. So there we go. Okay, and the next question, it says calculate the lattice enthalpy of calcium oxide. So when you're calculating the lattice enthalpy, it's a good idea to obviously use the cycle because that will help you. So the lattice enthalpy, if I bring the cycle back in here, the lattice enthalpy of calcium oxide is this step here. So what we have to do is we're going from here to here. That's the way we need to work out. So all we do is we start from this point and we just work our way backwards to get to the same step here. So effectively what we're doing is we do minus 798. So because we're going against the arrow, we're going to change the sign. So it's minus 798. Let's put that back there. Okay, and if you pull it back again, so you've got minus 798 going along here. Because we're going against the arrow back up here, that's going to turn into plus 141. So put that on there. And then bring it back. And you can see all the way down here, we're going against the arrow because we need to work our way down to the product. So we're working against this arrow, so that's going to be minus 1145. And then the next one is minus 590 because we're going against the arrow. And the next one is minus 249. And then the next one is minus 178 because we're still going against the arrow. And then the last one here, this one is with the arrow, but it's a minus anyway, so it's another minus. It's minus 635 because we're going with the arrow this time, so we don't need to change the sign. So put that there. Okay, so if we put all of that into our calculator, we should get an answer of this. Let's pull the calculator back in there. Right. So put that there so we can see it. Okay, so it's going to be minus 798 plus 141 minus 1145 minus 590 minus 249 minus 178 minus 635, and we should have minus 3454. There you go. And there's our answer. Okay, so the marks, we get 2 marks for this. So you get 1 for your working out. So you put 1 there to always show you're working, and then 1 for your answer. Although if you have the correct answer, you would get both marks. But it's useful to show you're working just in case you didn't get the right one at the end. Okay, right, and the last question of this, or the last part of this question, it's quite a big question. So it's part C. It says describe and explain the factors that affect the values of lattice enthalpies. Right. So we need to talk about the size of the ions here. So effectively we've got the size of the ion, and then we've got the charge of the ion. Because remember, it's ions that are effectively attracted to each other, and that actually makes sure that the ion is the whole lattice structure is held together. So the things that we need to look at is ionic size. And the smaller the ionic size, the more these ions can compact together and the less shielding we have. So that means we have a stronger attraction between oppositely charged ions. So that means the lattice enthalpy is going to be more negative. So the first point we need to write down, I'll just number these as well, is a decrease in ionic size. Means increased attraction, or we can say we have a more negative lattice enthalpy. There you go. So there's the first one. So smaller ion means that we have less shielding, so therefore the attraction between opposite charged ions is going to be stronger. And then the second one, I suppose we can also say, is about the increase in charge density. So I'm going to put that there. So this is basically the amount of charge there is per area of the actual ion. So for example, an ion that's really small with a big charge in it is going to have a stronger attraction with an opposite ion. So therefore the amount of energy needed to break up that lattice is going to be greater. So therefore you're going to get a more negative lattice enthalpy from this. So actually the increased nuclear charge density, has an impact. So we'll put here hence increased attraction. And we could say more negative lattice enthalpy. All right, so oops, mistake. Okay, so this is for 3 marks, and effectively the examiners are looking for ion. You've got to use the word ion here because we're talking about lattice enthalpies, which are ionic compounds. So we've got a decrease in ionic size. There's your first mark. And then an increase in charge density is your second mark. These are the things which would affect the lattice enthalpy. And the third mark is just coming up with some kind of link between the actual factor and the fact that we have a more negative lattice enthalpy. You can see these ones are actually the same. So you actually get 1 mark for making that link there. So that gets you the 3 marks altogether. So that's question 1 done. On to question number 2. Okay, so this is question 2. It says in aqueous solution, benzene diazonium chloride, C6H5N2Cl, decomposes above 10 degrees Celsius. So we've been given the equation here at the top, and it says a student investigates the rate of this reaction using an excess of water at 50 degrees Celsius. The student takes measurements at intervals during the reaction and then plots his experimental results to give the graph shown below. So you can see we've got a graph here, and the graph shows us the concentration of our benzene diazonium chloride, which is one of our reactants, and it shows it obviously depleting over time. Okay, so the first question, it says the student uses half-life to suggest the order of reaction with respect to C6H5N2Cl. What is meant by the half-life of a reaction? So this is just a standard definition that you need to know, and it is the time for concentration of the reactant to fall to half the original value. So the two bits really to this answer. One is the time element for it, for the concentration, but also for it to fall to half the original value. It is half-life, so you've got to include them terms there. So this is a definition that you just need to try and remember. And again, this is for 1 mark, so you get 1 mark for that. So pretty straightforward. Okay, so the next question says confirm the order of reaction with respect to C6H5N2Cl. Show you're working on the graph. So we've got 2 marks here. Now it does say show you're working on the graph. So in order to work out the order, we need to work out what the half-life pattern is. So if I go back up towards the top, so half-life, like we said before, was the time taken, or the time for the concentration of the reactant to fall to half the original value. So what we're going to do is we're going to start at the top here, and you can see that this is coming in at about 5.8. So if we find half of that, that should be around about the 2.9 area. And so we're going to draw a line using a ruler. We're going to find the 2.9, which is somewhere around about here. We'll draw a line going across, and then we're going to draw a line going down. Okay, now that comes out round about the 52 mark, somewhere around there, and we're going to find half of that again, which is this 2.9. So this is going to be roughly round about 1.5. So we're just going to draw a line going across to 1.5. And you see that comes out at 102. Now the exam board will accept a half-life of between 50 and 56. So you can see here that we've got the first one here, and this obviously lands between 52. So that's fine. So that fits between there. Now you can see that the gap here is from 52 to 102. It's a pretty even gap. We've halved the concentration, and the time taken has pretty much nearly doubled, just about. So what we can deduce from that is effectively that the order is first order. And that's because you have to put your reason as well, as the half-life value is constant. So in other words, it's increasing by the same amount, so it's not disproportionate. Okay, so you get 2 marks for that, and the first mark obviously comes in by showing your half-lives on there. So we'll put the marking point on there, and then you get obviously your other mark is for just mentioning the order of the reaction, which is first order. Okay, so on to the next question, the next part of the question, should we say. Okay, so okay, so we'll pull that down so we can see it. So it says, what would be the effect, if any, on the half-life of this reaction of doubling the initial concentration of C6H5N2Cl? So the effect of doubling the initial concentration on the half-life is no effect. The half-life is not affected by this, so let's put no effect. Okay, so that's just for 1 mark. And then B says the student predicts that the rate equation is rate equals K, and then the concentration of C6H5N2Cl. Using the graph and this rate equation, determine the rate of reaction after 40 seconds. and you've got to show your working on the graph. Okay, so what we've got to do is we've got to find the tangent at 40 seconds. So we're going to bring the graph back in here, and so what we're going to do is we're going to take the tangent at about 40 seconds. So you can see that's roughly about the same. There's the 40 there, that's the line. So we're going to draw our tangent there. Okay, and you see this is coming out at about 5.2 for the concentration, and the time's coming out at about 116, which is there. Okay, because that's going to be important when we're working out the actual rate. And the rate is always the tangent as well, as well as the gradient. Because this is a curve, then we have to draw a tangent against the 40-second mark, which is there. There's your 40 seconds. So in this case, to work out the gradient, it's the change in y over the change in x. So that's 5.2 divided by 116. So we're going to write that down into there. So the rate equals, and that's, we've got 5.2 divided by 116. Okay, and then if we bring in our calculator, we put that in, 5.2 divided by 116, and we should get 0.0448, but if we round that to 2 decimal places, so that's 3 decimal places, sorry, 2 significant figures, so that's going to be 0.045. And then what we have to do is we then have to work out our units as well. And so obviously we'll put the answer in there, 0.045. So the units for this is in moles per dm cubed, because that was the concentration of our C6H5N2Cl. And then this was time, so that's moles per dm cubed seconds, and that's the units. That's how you work out. That's always the units for rate as well for this case. So okay, so you get 3 marks. You actually get 1 mark for the tangent that's drawn on your graph. So give that a tick. You get 1 mark for the answer, and then 1 mark for the units, and that's how important the units are. You actually get 3 marks for this. So pretty important. Okay, so next one then says calculate the rate constant K for this reaction and give its units. So the rate constant K is basically the rate divided by, which is this over here. So if we come back to this, you can see the rate constant is K. So if we rearrange that, it would be rate divided by your concentration. So the rate we've actually just worked out here. Now, depending on what your answer is here, the exam board will have a slight tolerance here of about 10%. So depending on what this answer is, you should use this answer in this one here. So don't be tempted to change it, even if you don't think it's quite right. You actually get marks still for it, for the working out. So effectively the rate constant, K, is the answer to B part 1, which is this one here. In this case, I'm going to use 0.045. I'm going to divide that by 3.45. And I'll tell you why. Because if we look at if we bring this back in again, you can see at 40 seconds, which is here, if we go along, we should get about 3.45 around there. It hits it right in the middle there. So that's 3.45. They would accept, again, there'll be some leeway with this as well. So make sure that you can, it should be around about the 3.4 to 3.5 mark. So up here, so it should be round about there, 3.4 to 3.5. Make sure you get it between them lines there. Anything outside of that is not very accurate, so you've got to make sure you get that one right. So I'm going to put it right down in the middle, which is 3.45. And therefore, if we put that into our calculator, so we put that up there, so it's 0.045 divided by 3.45, and we should get 0.0130. But if I do that to 2 significant figures, that's going to be 0.013. So 0.013, and that's for K. And the units, because this was this top one here was our rate, which is moles per dm cubed per second, and this bit down here was the concentration of our chemical, so that's just moles per dm cubed, then effectively these ones will cancel out, and what we're left with is just s to the minus 1. So our units is just going to be s to the minus 1 in that case. And you get 2 marks for this. So you get 1 for this one, and 1 for your units as well. So 2 marks in total. So again, not too bad. Okay, and then part C. So the order of this reaction with respect to H2O is effectively 0. Explain why. And the main reason is, if we come back to this question over here, come back to this bit at the top, it said that we're using an excess of water right at the start there at 50 degrees. So the reason why the order of reaction with respect to water is pretty much 0 is because we have so much of it. It kind of overwhelms the concentration of everything else. So what we need to say is we say it has a very large concentration of H2O, or you could simply say there's an excess, and so because we have so much of it, we can say that effectively the order is 0. It doesn't matter how much more we add, it's not going to have any effect on our overall rate. But there we go. There's question 2 done. Nice, simple, 10 marks. You get 1 mark for that one as well. Let's put that one on there. So yeah, on to the next question. Okay, so this is question 3. And it says hydrogen and iodine react together in a reversible reaction. So we've got H2 plus I2 will give 2Hi, and they've given us the enthalpy change as well, which is minus 9 kilojoules per mole. So the chemist mixes together 2 times 10 to the minus 3 moles of H2 gas and 4 times 10 to the minus 3 moles of I2 gas in a 1 decimeter cubed container. So that makes our calculations a bit easier as well. The chemist seals the container. The mixture is heated and left to reach equilibrium. So at equilibrium, the mixture contains 3 times 10 to the minus 4 moles of H2. Calculate the equilibrium constant, Kc, including units, if any, for this equilibrium, and give your answer to 3 significant figures. So this precision bit is really, really important. When they ask for 3 significant figures, you must give it to 3 as well. Okay, so what we're going to do is we're going to start and write out our equation, and I'm just going to write it out again. Again, you can do this in loads of different ways, but this is just one method I think certainly I prefer anyway. So I'm just going to rewrite out the whole equation. So this is obviously talking about equilibria, and so what we need to do, what makes it a little bit easier, is I'm going to put start equilibrium on there, and then we're going to put equilibrium, on the bottom there. Okay, so the number of moles of hydrogen that we started with was 2 times 10 to the minus 3. So I'm going to put that on there. Okay, and the number of moles of iodine we had was 4 right at the start of the reaction. This is before we've mixed anything at all. So it's 4 times 10 to the minus 3. And then the number of moles of Hi, obviously at the start, is going to be nothing. We haven't made anything yet. So what we're going to do is we're then going to work out how much we have at equilibrium. Now it's told us that we have at equilibrium, the mixture contains 3 times 10 to the minus 4 moles of H2. So you can see there's our H2. And so 3 times 10 to the minus 4, I'm going to change that to the minus 3. I'm going to kind of break a rule of standard form and actually make this number less than 1, but it makes it a lot easier to kind of see. So all I have to do to turn that into a minus 3 like the rest of them is to basically move the decimal point back 1 place. So that's going to be 0.30 times by 10 to the minus 3. Okay, right, so now what we need to do is we need to work out Kc. Now Kc is the is basically the reactants, or the number of moles of concentration of reactants, products over reactants here. So we need to work out the equilibrium moles of iodine and Hi as well. So to do that, we need to work out the difference here. So how much has this dropped by? Because this has been used up. This is a reactant. So all we do is we pick up our calculator and we put the 2 numbers in, and we're going to subtract them away from each other. So we're going to put 2.00 times by 10 to the minus 3. And we're going to subtract that away from 0.30 times by 10 to the minus 3. And we should get a drop of 1.7 times by 10 to the minus 3. So we're going to put that in there. So this is a drop of 1.7 times by 10 to the minus 3. Okay, so if this drops by 1.7 times 10 to the minus 3, then so does this one as well, because these were 1-to-1 molar ratio. So this drops by the same amount. So I'm going to draw an arrow down there as well. So we're going to subtract that from 1.7 times by 10 to the minus 3. And that will tell us the number of moles at equilibrium. And in this case, the number of moles equals concentration because the volume is 1 decimeters cubed. So that's why I said it makes it a little bit easier to work out. So it should be useful. So 4 times 10 to the minus 3, we're going to subtract 1.7 times by 10 to the minus 3 away from that. That leaves us with 2.3 times by 10 to the minus 3. So put that in there. So it's going to be 2.3 times by 10 to the minus 3. Okay, and because these have dropped, this is double though. This would increase because these are being used up. These are reactants. This is a product, so that's being produced. So this has to increase by twice as many moles as this one decreased. So this one, I'm going to draw an arrow going down there. This one is effectively going to be 2 times by, because we've got double the mole, but we're going to increase it by 1.7 times by 10 to the minus 3. Okay, and therefore if we do that, we should find out the number of moles of HI at equilibrium. So we're going to do 2 times by 1.7 times by 10 to the minus 3, and that gives us 3.4 times by 10 to the minus 3. Go. So we'll put that in there. 3.4 times by 10 to the minus 3. Okay, so here's our equilibrium values. So equilibrium of H2, how much we have of I2 and how much we have of HI. So now what we need to do is write in our Kc expression, and it's products over reactants. In this case, the number of moles equals the concentration as well, because it's at 1 decimeter cubed container. So Kc, let's put that there, Kc equals, and we've got this value here, which is 3.4 times by 10 to the minus 3, and that's going to be squared, and we're going to divide that by 0.30 times by 10 to the minus 3, and multiply that by 2.30 times by 10 to the minus 3. Okay, so if we then put that into our calculator, now I've worked this one out previously just to save a bit of time, then we should get a Kc value of 16.8, and the units in this case we can work out really simply by looking at this. Now this squared here is there because we have 2 HI, but this is the concentration. So this is moles per dm cubed, moles per dm cubed. So if I write them out there, that's moles per dm cubed. Effectively, we've got double the concentration because we've got the 2 there, and the units here is exactly the same. So that's moles per dm cubed for this one, and that's the concentration of iodine. So that's moles per dm cubed as well. And then obviously we're dividing them; they'll all cancel out. So the units for this is nothing because we don't have any units. So the units is none. We don't actually have any units whatsoever, which may seem a bit odd, but that does happen if all your the units actually cancel out in your equation. So there's a lot of marks here. There's 5 marks for this question, and the marks come in very simply by, so if I nudge that back up again, you get a mark for this answer. There's 1. You get a mark for this answer. That's your second one. You also get a mark for your equation and making sure you're writing it correctly. You get a mark for your answer, and you get a mark for stating the units. So a good chunk of marks there. And I think this method is quite neat because it shows you exactly what you've got from start to equilibrium, and you can see clearly. Right, okay, so on to the next question. Next part of the question, I should say. It's question 3. Right, so let's move that over here. All right. Okay, let's nudge that down so we can see it. So it says the chemist repeats the experiment several times. In each experiment, the chemist makes one change. The chemist uses 3 times 10 to the minus 3 moles of H2 gas instead of 2 times 10 to the minus 3 moles of H2 gas. Predict whether the amounts of H2 gas, I2 gas, and HI gas in the equilibrium mixture would be greater, smaller, or the same as the original experiment. Answer by placing the ticks in the appropriate boxes of the table below. Right, so the first thing we've done is actually we have increased the amount of H2, because we did have 2 times 10 to the minus 3, and now we've got 3 times 10 to the minus 3. So effectively that means we have a greater amount of H2 at equilibrium because we had more of it at the start. So that's going to be greater. However, the H2 reacts with the iodine. Because we've got more H2, it'll react with a little bit more of the iodine. We haven't changed the iodine at all, so actually we're going to have slightly less iodine as a result. So that should be smaller. As a result, because overall we're producing a little bit more, the iodine's been used up more, but we've put in more hydrogen than compared to at the start. We should end up with more hydrogen iodide as a result. So you get 2 marks for this. Obviously you get both marks for having all 3 boxes ticked, but you would get 1 mark if you only had 2 boxes ticked correctly. So, but then you get 2 for obviously all 3. So yeah, so make sure you can kind of understand that one. It's a bit of a funny one, that. Okay, then part 2, it says the chemist heats up the mixture of to a higher temperature at constant pressure. Explain whether the value of Kc would be greater, smaller, or the same. Now these are classic questions. They always come up, and the key thing is really the only thing that would affect Kc is temperature. So this is talking about a a higher temperature, but the pressure is the same. Now what we have to do is look at our Kc expression here. Now what we need to do, if we look at our equation back, you can see this reaction is exothermic overall, going from left to right. So if I increase the temperature, then it's going to shift in the endothermic direction, which means equilibrium will shift to the left, and so therefore we will have more reactants than we will products. So if we come to our Kc expression, if we increase the bottom line, remember the bottom line represents the reactants. So if we had a bigger value on the bottom, what that means, if you see this like a fraction, if you divide by a bigger number, then your answer here is going to be smaller. So Kc would actually decrease as a result. So if we come back to this question here, Kc would decrease, and the reason why is because the forward reaction is exothermic. Now you need both parts to get the mark for this. If the reaction was endothermic going forward, then Kc would increase. It would just be the complete opposite. But yeah, you only get 1 mark for that. So you do need to put both things, because it does say explain whether the value of Kc. So you can't just say whether it goes up or down. We've got to say why as well. So that would get you obviously that mark there. And then the last part to this question says the chemist increases the pressure of the mixture at constant temperature. Explain whether the value of Kc would be greater, smaller, or the same. Now, like I say, the only thing which affects Kc is the temperature, so any change in pressure is going to have no effect. So Kc would be the same in this case. Okay, and again, the reason is what I said. So Kc only changes with temperature. Temperature, there you go, not pressure. And that's it explained. 1 mark again, so you need both parts because it did ask for an explanation. There you go, tick, 1 mark, fantastic. Right, okay, so there you go, 9 marks. Equilibria, very classic question, especially these last 2. You know, they're pretty standard then. And make sure you can work out equilibria, Kc constants as well. Okay, that's it. On to the next question. Okay, so this is question 4, and this is a massive question. There's 22 marks in total for it, so plenty to get, plenty of marks to get for grabs. So we'll start with this question here. So it says this question looks at pH values and reactions of acids, bases, and buffers. 0.14 moles per dm cubed solutions of hydrochloric acid HCl and chloric 1 acid HClO with a pKa of 7.43 have different pH values. Explain why the pH values are different and calculate the pH of 0.14 moles per dm cubed solutions of HCl and HClO to 2 decimal places. Show any working in calculation. So we're starting off with a massive 5-mark question. So the first thing we need to do is identify which ones are strong and which ones are weak. And then obviously we need to work out the pH values of each. So the strong acid is the HCl. That's the strong acid. So we're going to start with that one first. So we'll put on here, so HCl is a strong acid, and HClO is a weak acid. So we actually get a mark for just stating that fact there. And then what we have to do is obviously calculate it. So first of all, we're going to calculate the pH of HCl first. So because it's a strong acid, we can assume that it fully dissociates. And so therefore the number of moles, or the concentration of H plus ions, will equal the concentration of the HCl to start off with. So that makes the calculation really easy, because all we have to do is we go straight in for pH equals minus log of the concentration of H plus ions. This will equal the concentration of the acid, which we've got up here, which is 0.14 moles per dm cubed. So all we do is we put in our equation, we put minus log of 0.14, and we should get our answer. Let's put the calculator over here. So it's the minus log of 0.14, and we should get 0.85. There you go. There's your first one. So there's your HCl. And then the next one, HClO, is not quite as straightforward. It's a weak acid, so we have to use Ka. But the problem is we don't have Ka either. But what we do have is pK, which is up here. So pK is 7.43. So what we're going to do is we're going to work out what Ka is. Now Ka is just the anti-log of pKa. So effectively, when you put it in your calculator, which we'll show you in a minute, you'll see a little 10, and it's the minus pKa, so it's 7.43. So when you put it into calculator, you put shift log, and then you put minus the pKa, which is 7.43, and you'll see that when I put it in here. So I'll just move the calculator up so you can see it. So this is going to be shift, and then you put log minus 7.43. And that should get you 3.72 times by 10 to the minus 8, or I'm just going to put 3.7. Okay, and that's the Ka value. And then once we've got Ka, we can then use it in our Ka expression to work out the pH. And to work out pH, we need H+. So we're just going to write the Ka expression here. So Ka will equal, now this one we can assume that H plus and OH minus, they equal the same. So we're going to put squared on the top, divided by the concentration of Ha, which is your concentration of your weak acid. And we can rearrange that, and we can get H plus squared will equal the Ka value, which is 3.7 times by 10 to the minus 8. And we're going to multiply that by the concentration of our acid, which was 0.14, which is up there at the top. Okay, and then if we put that into our calculator, we should get, so if we put in 3.7 times by 10 to the minus 8 times by 0.14, and that gives us 5.18 times 10 times by 10 to the minus 9. But remember, that's h plus squared. And so therefore what we need to do is we need to do the square root of that to find out the concentration of H plus. So if we take the square root of that, square root of 5.18 times by 10 to the minus 9, that will give us 7.19, so or 7.20 times by 10 to the minus 5. So we'll put that on there. Times by 10 to the minus 5. And that's obviously moles per dm cubed. And then now, because we've got H plus, we can then work out pH. So pH equals the minus log of this value here, that's your H plus, 7.20 times by 10 to the minus 5. And if we put that into our calculator, we should get, so it's minus log of 7.20 times by 10 to the minus 5. And that should get us 4.14. And there you go, and there's your answer for the pH. So 5 marks, decent number of marks. Let's see whether we get the marks from. You get 1 mark for talking about that it's an acid, that HCl is an acid and HCl is a weak acid. You get 1 for working out the pH, obviously, of HCl. You get 1 for working out the Ka value. So there's 1 there. You get 1 for working out the, for showing the working for your square root. To work out H plus, and obviously get 1 for the answer as well. So there's your 5 marks. Okay, right, big question. Okay, so the next one, it says aluminium powder is added to aqueous ethanoic acid, which is your weak acid. Write a full and ionic equations for the reaction that takes place. Okay, so the full equation, this is just an acid base, an acid metal, sorry, reaction. So we're going to put Al, and we're going to add that to CH3COOH, because that's our weak acid. And acid plus metal will always give salt plus water. So the salt in this case is going to be this. So CH3COO3Al. We need 3 of these. These all have a 1 minus charge. And Al's got a 3 plus charge. So we need 3 of them to make sure that that balances. And we're also going to form H2 as well. Now we have to get this lot balanced. You can see we've got a 3 there, but we have 2 hydrogens there, or H2. So actually, in terms of balancing, we should need 2 aluminiums, and we'll need 2 of these as well to make sure it all balances. We need 6 of them and 3 of them, which is H2. Okay, so that should give you your final equation. You can see acid plus metal gives salt plus hydrogen gas. That's always the case. And the ionic equation is basically all we're interested in is aluminium reacting with the acid. The acid, the only important part of the acid is the H plus. So we're going to write this down here. So it's 2Al, and that's going to react with 6H plus, because that's the ions that are important in the acid. And we're going to form 2 lots of Al3 plus, because that's the ion that we're looking at. Obviously plus your 3H2 as well. Okay, so pretty straightforward reactions. The balancing might take a little bit of time to do, but yeah, 1 mark and 1 mark. There you go. So it's 2 marks individually. Okay, right, next part. Okay, so then it says calculate the pH of a 0.4 mole per dm cubed solution of sodium hydroxide. So because it's an alkali, we have to use the Kw expression. So Kw, and then because Kw actually contains H plus. Remember, if we want to work out pH, we need to work out H plus. So that's really, really important. And OH minus. So to work out the pH of an alkali, we need to use the Kw expression. So if we rearrange that, we can get the H plus bit. So like this. So the concentration of H plus is going to be Kw over the concentration of OH minus. And so if we write that, it should be 1.0 times by 10 to the minus 14. Sorry. This is always the case. The value of Kw is always the case at room temperature and pressure, and that's what we're assuming here as well. Okay, and the concentration of OH minus is 0.4. That's just here. Because it's a strong base, so we can assume that the concentration of sodium hydroxide equals the concentration of OH minus. So that's just going to be 0.4 in there. And so therefore the concentration of H plus is going to be, let's put that in our calculator. So it's going to be 1.0 times by 10 to the minus 14 divided by 0.4. And that's going to be 2.5 times by 10 to the minus 14. There you go. Okay. And so therefore the pH is going to equal, put that in there, so it's going to be the minus log of your H plus, which is 2.5 times by 10 to the minus 14. And so that's going to be minus log times by 2.5 times by 10 to the minus 14. Oops, put that again. So the minus log of 2.5 times by 10 to the minus 14 should be 13.6. There you go. Okay, so 2 marks for this. The marks come in for 1 for calculating your H plus, and obviously 1 for your answer as well. So there you go. Those are 2 marks. Okay, right, next question. This is a big question. See, this one's 7 marks, so it's a big question. Right, so we're going to start. It says, in biochemistry, buffer solutions based on methanoic acid can be used in the analysis of urine samples. Explain what is meant by the term buffer solution and describe how a buffer solution based on methanoic acid can act as a buffer. In your answer, you should explain how the equilibrium system allows the buffer solution to control the pH. Right, so the first thing we need to do is obviously define what we mean by the term buffer solution. So you get 2 marks for this, and basically a buffer resists any change in pH when a small amount of acid or alkali are added. Okay, so that's really important. It resists any change. It doesn't just stop the pH change, and it resists it. So that's really important, and only does that if it's a small amount of acid or alkali. If you go and chuck loads of acid or alkali into a buffer solution, it's obviously going to break the buffer. So it'd only do it with a very small change, but nonetheless still very useful. Okay, so we're going to one of the best ways I think of doing this is to draw down or write down 2 equations that show how a buffer works. Now, a buffer is made by taking a weak acid and its salt. So we don't know what the salt is here, but it doesn't matter. We're going to just write down the equations to show it. So we're going to put down, I'm going to put down the first equation here. Now this is the one showing, it is talking about methanoic acid. So methanoic acid is a weak acid, and so therefore it will dissociate to form this. Okay, but because it's a weak acid, it doesn't dissociate fully. So therefore what we have is we have actually quite a high amount of this, relatively speaking, and low amounts of these 2 here. Because it's a weak acid, it doesn't dissociate to produce these very much. Now, the salt that we make, the salt is pretty straightforward. It's just the salt of this. So what I'm going to do, the salt would normally be like a group 1 metal or something like that. I'm just going to put M to represent our salt. So it's the salt of this acid here. And this will actually, salts are very good at dissociating. So what you form is you form a lot of this. M plus, that's just the metal. Again, that's irrelevant. So because it's a salt, it dissociates fully. So actually we have, relatively speaking, we have low amounts of this, but we actually have high amounts of these 2 at the end there. Okay, and this is going to play a role because it's going to help us to explain what happens with our buffer. Okay, so let's start with, let's say if we add an acid first. So we need to give the scenario of how the buffer works when we add an acid and when we add an alkali. So when we add an acid, the acids obviously contain H plus ions. Okay, now out of these, imagine this is in one beaker. This whole thing is existing in equilibrium in one beaker. If we take our H plus ions, these will react with the HCOO minus ions. We have a high amount of these, so that's pretty good. So the H plus ions, these will react. These will react with the HCOO minus ions, which are there. And so what effect that has is that equilibrium will shift to the left. And what you'll make is you'll make more HCOOH. So effectively what's happening is if you imagine these two reactions kind of interlink, they're all in the same beaker. So the H plus ions will react with this. If you add the H plus onto there, you would actually form this, which is your acid back again. So effectively it's shifting left. And we can interlink these equations as well to explain this. So that's what happens when we add an acid. Now, if we go on to the next bit, and if we say we're going to add an alkali this time, so what we're going to do is we're going to have OH minus ions. And we need to say what these react with. So you can see OH minus ions will actually react with the H plus ions here. Now it could react with them, but that would form a metal hydroxide, which is soluble. So it would just decompose again or break up, and it will dissociate, and it will form that back again. So actually, what it does is it will react with the H plus ions. We have a low amount of these though, so there isn't a great deal of them to react. So what happens is we need to talk about equilibrium here, or Le Chatelier's principle. So if the OH minus, they will react with the H plus ions. Okay, and then what we need to say is that equilibrium will shift right, and this is to replace the lost H plus ions. So effectively it's really clever. The OH minus reacts with this, but because we have a high amount of our weak acid, this actually replaces them and puts them back. And this is very common. This is exactly how a buffer works. So writing down two equations for your weak acid and then the weak acid salt, and writing down the high and low will help you to kind of work out what happens when an acid is added and when an alkali is added. You can see loads of marks here, so definitely worth understanding and making sure you're getting it right. In terms of the marks and where they come from, you get one mark for saying the buffer will resist any change in pH. You get one for saying only when a small amount of acid or alkali is added. You actually get one mark for the equation for the acid in particular. The alkali one, the salt one here, is just there to help explain what the buffer is there for. You actually get one mark for saying the H plus ions react with the methanoate ions, which are these ones here. And you get one mark for explaining what happens with equilibrium. And it's exactly the same with the alkali. One mark for saying what the OH minus does react with, and one mark for saying what happens at equilibrium. So you see you've got 1, 2, 3, 4, 5, 6, 7 marks there in total. So a good chunk of marks. So definitely worth making sure you get this right. Okay, on to the next section. Okay, so this is the last part of this question. So this is question part 2, and it's got 6 marks. Again, a big number of marks here. It says a chemist prepares a buffer solution by mixing together the following: 200 centimeters cubed of 3.20 moles per dm cubed of methanoic acid, and we're being given the K value, and 800 centimeters cubed of 0.5 moles per dm cubed of sodium hydroxide. The volume of the buffer solution is 1 decimeters cubed, because obviously we've got 200 and 800, so that's fine. That'll make the calculation a bit easier. Explain why a buffer solution is formed when these two solutions are mixed, and calculate the pH of this buffer solution, and give your answer to 2 decimal places. So this is a pretty tricky question actually. So what we're going to do is we're going to write down how it's formed first. Now remember we said in the last question that a buffer was a weak acid and its salt mixed together. Now here we've got a weak acid, but we have a strong base. So we need to kind of say, how does this mixing these form our weak salt? And it's really simple. We've got HCOOH. I'm going to react that with some sodium hydroxide, and that will form HCOO minus Na plus. There's your salt, bingo, and then H2O. So what we say is actually all of this will react to form your salt, so none of this will be left behind. But actually, to have a buffer, we must have the salt, which is what we need, but we must have some acid left. So what we need to say is actually some weak acid remains. In other words, we have an excess of this. So we have loads of this in mole terms. Relative to this, we shouldn't have much. So all of this will react to form that, and then you'll still have some of this left over. So that's our next comment that we need to say, really, is some weak acid remains. And that's really important because that's exactly how you would make your buffer solution. Okay, right, so then what we need to do is we now need to work out the pH of the buffer solution. So the best thing, it's a big calculation this, but the best thing to do is to work out the moles of everything that we have before. Now, the first thing we'll do is we'll work out the number of moles of the weak acid first. This is before we've actually mixed them. So we're going to start by writing this here. So moles of the HCOOH before mixing is literally just your 3.20, and this is the concentration, times by the volume, which is 200. Now I'm just going to put times by 10 to the minus 3 because that basically means divide by 1,000. So I've converted that into decimeters cubed by doing that. So if I put that into my calculator, so we have 3.20 times by 200 times by 10 to the minus 3, and that should give us 0.64. Okay, and so this is obviously moles. And then what we need to do is work out the number of moles of sodium hydroxide before. Again, this is like before we mix them. So the number of moles before is going to be 0.500, because that's the concentration, times by the volume. In this case, it's 800. To convert that to decimeters cubed, we're going to times that by 10 to the minus 3. So that converts it to decimeters cubed. And then if we put that in our calculator, we should get 0.500. Oops, 0.500. We're going to multiply that by 800 times by 10 to the minus 3. And that gives us a number of moles of 0.4. Okay, right, so once we've done that, we then need to obviously work out what's in excess. You can see here that we've got more moles of acid than we do sodium hydroxide, so that's fine. All of this will react and none will be left behind, and it will react with this. But only 0.4 moles of this will react with this, because obviously we've got more of this. You can see we've got an excess. So we're going to work out that excess now, because that's actually quite important. So we're going to put there. And because this is in decimeters cubed, we can also say that this is the same as the number of moles as well. So we can work out the excess of HCOOH, and this is really easy, because all you do is you do 0.64, that's the number of moles of your weak acid, take that away from the number of moles of alkali that's reacted with it, and obviously you won't need a calculator for that, you can work that out as 0.24 moles. And because this is all in 1 decimeters cubed, that is actually the same as the concentration, 0.24 moles per dm cubed, because the volume is a decimeters cubed anyway, so that's going to be the same. So that makes the calculation a little bit easier. So the next thing we need to say is we need to work out, now we've worked out the excess number of moles, we'll come back to that one because that's an important one. We then need to say that actually the number of moles of sodium hydroxide equals the number of moles of your salt. Now, we need this because we're going to work out the pH of a buffer, and so we need the salt, the concentration of salt as well. So I'm just going to put HC. Now, this is sodium hydroxide, so the salt we've actually formed is this. So the number of moles of that equals that, because we assumed that it all reacts to form the salt. So that means, so I bring that kind of down here. So that means the concentration of HCOO minus Na plus, or you could say the concentration of HCOO minus. There you go. And that would actually equal 0.40 moles per decimeters cubed, because we assume that the amount of alkali reacts to form all the salt. So therefore the amount of salt produced, or these ethanoate ions, because the salt fully dissociates, is equal to the same amount. So that's 0.4 moles per dm cubed. Right, so now we have all these parts. We need this bit as well. All of these are at equilibrium, these two here. These were at the start, which we're not interested in. It's all the equilibrium ones. So what we need to do is we need to work out, because we need to work out pH, we need to work out H+. So using our Ka expression, we can rearrange this, and we can have H plus equals Ka, and we've got HCOOH, the concentration of acid, divided by the concentration of HCOO minus, and that's the ethanoate ion formed from the salt. That's why we had to work that out. And this is the acid at equilibrium. So in other words, what's left over, this is the excess. And then what we're going to do is we're going to stick that in our calculator. So that's going to be 1.70 times by 10 to the minus 4, and that's the Ka value. Multiply that by 0.24. That was the number of moles of acid in excess. Divide that by this bit here, which is the concentration of your salt, which is 0.40. Okay, there you go. And so therefore, if we put that in our calculator, 1.70 times by 10 to the minus 4, multiply that by 0.24, and then if we divide that by 0.40, we should get 1.02 times by 10 to the minus 4, and that's moles per dm cubed. Right, and that's the number of moles of our H+. And then finally, the last thing we have to do is obviously just work out pH. So pH equal the minus log of this number here, which is 1.02 times by 10 to the minus 4. And then if we put that in our calculator, it's the final thing. It's a big calculation, like I say. So it's minus log of 1.02 times by 10 to the minus 4, and that should give us a pH of 3.99. And let's just make that really clear. There we go. Phew. Big, massive equation. Okay, so we're going to assign the marks here. There is 6 marks, so again, a decent number of marks here. So these are going to make the difference between one grade and the other. You get 1 mark for your equation up there. You get 1 mark for saying that you have an excess, which is that some acid or weak acid remains, and that's actually demonstrated here. You can see there's more acid than there is alkali. You get 1 mark for working out the number of moles of acid that are in excess, which is that bit there. You also get 1 mark for working out the number of moles of alkali, which is that one there. So you get 1 mark there. And then if we come on to the last parts here, you get 1 mark for actually putting it into your Ka expression, which is there, and then obviously 1 mark for your final answer, which is at the bottom there. So you see you've got 1, 2, 3, 4, and then 5, 6 at the top there. Okay, so there we go, 22 marks in total. This is really, really important. Make sure you know this calculation here. So there we go, on to the next question. Okay, so this is question 5, and it says iron is heated with chlorine to form an orange-brown solution A. Solid A is dissolved in water to form an orange-brown solution X, containing the complex ion Fe H2O6 3+. Separate portions of solution X are reacted as shown in experiments 1 to 4 below. It says experiment 1, aqueous sodium hydroxide is added to solution X, an orange-brown precipitate B forms. Experiment 2, excess zinc powder is added to solution X and the mixture is heated. The excess zinc is removed, leaving a pale green solution containing the complex ion C and aqueous Zn2+ ions. Experiment 3, an excess of aqueous potassium cyanide, KCN, is added to solution X. The solution turns yellow colour and contains the complex ion E. E is a molar mass of 211.8 grams per mole. And experiment 4, an aqueous solution containing ethane diurate ions, CO-2, is added to solution X. A coloured solution forms containing a mixture of optical isomers F and G, and we've got the structure of the ethane diurate ion below. Okay, so the first question says write an equation for the formation of solid A. So if we go back up to the top, it says solid A is iron is heated with chlorine to form an orange-brown solid. So the orange-brown solid is iron chloride. So we just need to write the reaction there. So the equation is going to be Fe plus Cl2, and that will form iron chloride. This is FeCl3, and we need to balance that as well. So you can see that we need a 3 there, a 2 there, and a 2 there, and that should make it all balanced. Okay. So the next one, it says in experiment 1, write an ionic equation for the formation of precipitate B. So in experiment 1, so bring that down, aqueous sodium hydroxide is added to the solution X, an orange-brown precipitate form. So when we're taking the complex ion and we're going to add hydroxide to it, we're effectively forming this. And it's going to be an ionic equation, so we just need the basics. So we take the Fe3+, because that was the solution that we formed. We're going to react that with OH minus, and we're going to form iron hydroxide, so FeOH, and because it's a 3+, we need 3 of them, so we need a 3 stuck there as well. But that's the ionic compound, or the ionic equation, sorry. Okay, so the next one is part of these, so nice short equations. In experiment 2, write an equation for the formation of complex ion C. So if we come back to experiment 2, it says excess zinc powder is added to solution X and the mixture is heated. The excess zinc is removed, leaving a pale green solution containing the complex ion C and aqueous Zn2+ ions. So right, we're forming the Zn2+ ions. We're forming a pale green solution. So we're going from like a browny rusty colour iron 3 to pale green. Now pale green is iron 2. So effectively we have reduced our iron 3 complex to iron 2. But crucially we've got to form Zn2+ ions. So that's going to be important when we come to balancing. So if you come to the one at the bottom here, so we've got, let's write our equation out. So it's Fe H2O6 3+, and we're going to react that with the zinc metal, and we're going to form a very similar, well the actual complex is the same, so we've still got the 6 waters, but we're going to have a 2+ charge on the end. Now we're going to have zinc 2+. So the only way in which this can balance in terms of the charges is we need a 2 there, because that would give us a total of 6+ on this side, and we need a 2 there as well, and again that would give us a total of 6+ on that side. So yeah, you've got to make sure that that's balanced properly. I think without knowing that bit, you might have just left it without the 2. You actually get 2 marks for this, and 1 is for the balancing, so you actually get credit for the balancing there, and you get credit for obviously the reagents that you've written in as well, so that's 2 marks. Okay, and the next one says state the type of reaction taking place. So we have oxidation here, and we have reduction here, so this is a redox reaction, and that gets you the next mark. Okay, right, next question. Okay, so we have, it says in experiment 3, write an equation for the formation of complex ion E. So experiment 3, Let's quickly bring that back in there. Experiment 3 says an excess aqueous potassium cyanide is added to solution X. It turns a yellow colour to form complex E. So we're adding cyanide ions to this, and we're starting from our iron 3 plus. So we're just going to write the equation there. So this is Fe H2O 6 3 plus, and we're going to react that with our cyanide ions, Cn minus, and that's going to form Fe Cn6. So cyanide will actually displace all of the ligands. So it's going to be 3 minus now, because the cyanide's got a minus charge on it, and we've displaced 6 of them on there. And we form, obviously the waters have now been kicked off, so we're going to put water over there. Now 6 waters have been kicked off, and we needed 6 cyanide ligands to actually displace them. So watch out for the charge and make sure it's balanced. Again, it's 2 marks, 1 for the balancing, which is there, and we get 1 for the reagents as well. So you get 2 marks in total for that. Okay, and so the next one is says state the type of reaction taking place. So this reaction is ligand substitution. So we've substituted the water ligands for cyanide. So this is a ligand substitution reaction. Alright, okay, so the next one, it says in experiment 4, optical isomers F and G are formed. Show the 3D shapes of F and G, and in your diagram show the ligand atoms that are bonded to the metal ions and any overall charges. Right, so we've got 3 marks for this one. So we'll bring this one back in again. So experiment 4, like we said, was an aqueous solution containing ethane diorite ions, which is this one here. Is added to solution X, and a coloured solution forms containing a mixture of the optical isomers F and G. So if they're optical isomers, it means they're mirror images of each other. So we just need to draw 2 molecules that are mirror images, but we must show the actual structure of the ethane diorite ion. Now this is what we call a bidentate ligand. It means it bonds twice to the ion in there. So remember, iron can have 6 bonds surrounding it, the coordination number of 6. So that means this will take up 2 of them, so you can only fit 3 of these around. And you'll see what I mean when I draw the structure, because they're quite big ligands. Right, so we're going to start with drawing just very quickly. Let's put the Fe there, and it has to be 3D. So there's 2 going away, 2 coming towards you, and 1 in the plane of vision. So these are the oxygens from the ethane diorite, and all we're going to do is just join them together. So double bond oxygen, double bond oxygen. I'm going to join these 2 together and these 2 together. Okay, square bracket is a complex. And this has got your ethane diorite around it. Ethane diorite has 2 minus charges attached to it, so each one of these is 2 minus. The Fe in the middle was 3 plus, so if you've got 2 minus, a 2 minus, and 2 minus, that leaves you with a 3 minus charge up there. So you must include that charge there, because each ethane diorite is the same, has a 2 minus charge. Okay, so all we're going to do is we're going to just draw the mirror image of these 2. So I'm going to put Fe in the middle there, dotted line oxygen. I'm going to put the wedge one down there, which is going to be oxygen. And literally all I'm doing, I know it looks a little bit squint, but I'm just drawing the mirror image of that. You can see it's starting to form this mirror image. Even with my very, very bad art skills, you can still see that. Okay, so you see we've got this one here, and we're going to join them 2. This bit does take time, but it did say that you have to draw the whole thing. There you go. Square bracket around the side, 3 minus charge again. So you can see these are pretty much a mirror image. So this is what makes them optical isomers of each other, because they are the same molecule, but just optically they will take plane polarized light in a different way. So this is good. You actually get 1 mark for drawing that structure, 1 mark for drawing its mirror image, and you actually get 1 mark for the charges as well. You have to have both charges in place to make sure you get them marks. So that's where you get your 3 marks from. Okay, and then the last part says, in a separate experiment, iron metal is heated with potassium nitrate, KNO3, a strong oxidizing agent. A reaction takes place and the resulting mixture is poured into water. A dark red solution forms containing ferrate 6 ions. The ferrate 6 ion has a 2- charge. Suggest a possible formula for the ferrate 6 ion. So all we have to do is make sure that we have oxygen in there because it's an oxidizing agent, and the iron itself has got to have a +6 charge, but the whole thing's got to have a 2- charge. So that means the oxygen, we must have 4 oxygens because each oxygen is -2, so that would add up to -8. So that would give an overall charge of 2-. So there's one possible one. You could go for, again, for the same reasons, you can go for Fe2O7, 2-. Again, that would still give you a +6 charge for iron. As long as iron has a +6 charge, that's the main thing. But there we go. That's that question done. Question 5. On to the next one. Okay, so this is question 6, and it says the equation for the reaction of CO2 and H2O to produce glucose, C6H12O6, and O2 is shown below, and you can see here that we've got the equation. They've given us an enthalpy value and they've given us an entropy value as well for the full reaction. So say standard entropies are given in the table below. You can see here that we've got entropy values for different substances. So it says calculate the standard entropy of glucose. So all they want us to do is to work out obviously the entropy of glucose, but we have the total entropy of the reaction and the entropy of the other reagents here as well. So to calculate the total entropy, it is products minus reactants. So, but one of the products that we don't know, so all we're doing here is effectively just doing a little bit of algebra to work out what this unknown bit is here. So we're going to set it out just like that. So the total entropy was -256. So I'm just going to put that there. So the total entropy will equal, and now it's the products minus reactants. So one of the products we know is effectively 6 times by the oxygen value, which is 205. Let's put that there. Plus the total value for this. So this is the entropy of C6H12O6. And what I'll do is I'll call that X when we work them out later, minus the total entropy on the other side. So this is going to be 6 times by 214, and that's going to be for the carbon dioxide, plus 6 times by, and the water is 70. Okay, and so if we rearrange this, if we simplify, we'll have -256. And that's going to equal, now if we bring our calculator in and we do 6 times by 205, 1230. So we're going to put that there, 1230. Now we know that this, I'm going to call this X, so it's plus, I'll just call this X because it makes it a lot easier instead of writing all that out, minus, and then we want the total for this side, so that's going to be 6 times by 214. Press equals, okay, and we're going to add that to 6 times by 70. We should get 1704. Okay, which is on that side. Now, if I combine these two numbers together, so if we do -256 would equal, and then if I do the 1230 again to simplify it, minus 1704, and we should get -474. So I'll put X minus 474, and then all we have to do is take this across and add the two numbers together. So we're going to have -256, take this across, that's going to be plus 474 equals, we should get 218, and that is our answer there. Okay, so yeah, just a little bit of algebra there. It's not too bad, I suppose. The 2 marks you get for this, you get 1 mark for actually working out that bit there, and obviously 1 mark for your answer as well. So not too bad. Okay, so the next bit It says calculate delta G in kilojoules per mole at 25 degrees Celsius and show your working. Right, so delta G, the equation, this is Gibbs free energy. Delta G equals delta H minus T delta S. Okay, so if we put all them numbers in, and again we've got to be careful because we need to work it out in kilojoules per mole. So the delta G is the enthalpy, which is 2879, which is that number up there. That one, at the top there. Go 2879. So that should be 2879 minus the temperature this was at was 298, because it's, if we convert that into Kelvin, that's going to be minus 298. And then we're going to multiply that by the change in entropy. Now the entropy we were given, if I come back up here, is actually in joules per Kelvin per mole, but we need to work it out in kilojoules, so I need to convert that to kilojoules. So if I move it back, decimal point back 3 places, we should get that into kilojoules. So that's going to be minus 0.256, and obviously this bit's in kilojoules. Okay, so that's really important to do that, because if you miss that bit out, your number will come out far too big. And then if you put all that in your calculator, we should have 2879 minus, and then we're going to do, if I get rid of that, 298 times by minus 0.256, and we should get our final answer to be 2955. So put that in there, 2955, and that is in kilojoules per mole. So that's fine because we converted this one to kilojoules at the top here. So again, 2 marks, 1 for that one and 1 for that one. So you get 2 marks. Okay, and the next bit says explain why this reaction is not feasible at any temperature. So you have to actually explain quite a lot here for 1 mark. But the idea is that you look at this kind of equation here. Remember, if delta G is positive, that means the reaction isn't feasible. So what we're looking at is the 2 halves. We're looking at the delta H half and we're looking at the T delta S half. And what we're saying is that actually the delta H is positive. So this is an endothermic reaction, which is not favorable really anyway. So this is positive, and the T delta S bit is always going to be negative in this case, because we've got a minus and a minus, which is going to give us a plus. So if this is positive if this is positive and this is negative, then this is always going to be positive, which means the reaction won't be feasible regardless of the temperature that it's going to be at. So if we put this here, which is a bit weird because this happens in plants as well. So, but anyway, let's put the explanation down. So we just need to say that delta H is positive, and the T delta S part of the equation is negative. So that means delta G will always be positive. There we go. So yeah, that's how you work it. 1 mark for that one. So again, you don't really get much for that. Okay, right, and then on to the last section of this question. So it's a nice short one. It says, although the reaction between carbon dioxide and water to form glucose and O2 appears not to be feasible, plants are able to make the reaction take place spontaneously by photosynthesis. So each year, 3.4 times 10 to the 18 kilojoules of solar energy is taken in by all the plants on the earth to make photosynthesis take place. Calculate the mass of carbon dioxide that is removed each year from the atmosphere by photosynthesis on Earth. Ooh, so this is a tough one. Right, so what we have to do is, it is asking us to work out the mass of carbon dioxide that's removed. Now, to work out the mass, we need to know the number of moles of something. Now, what we do have from this reaction is we do have the enthalpy change for this reaction, which is in kilojoules per mole, Now we have an energy value here of kilojoules. Now if we can write an equation that combines these two to leave us with just moles, we'll be able to work out the mass of carbon dioxide produced. And so what we can do is, if we take our energy value, which is this one here, now we actually, if we go back to this equation here, you can see that actually we produce 6 loads of carbon dioxide is used in this one photosynthesis reaction. So what we have to do is we have to take the energy value here taken in by the plant and multiply it by 6 to represent the 6 loads of carbon dioxide that's needed to photosynthesize. So the first thing we're going to do is do 3.4 times by 10 to the 18 and multiply by that by 6. And this is in kilojoules, this bit here. And then we're going to divide that by, now the enthalpy value was 2879. So this was the enthalpy that was for photosynthesis. So it's a plus value. So that's going to be 2879. And the units there are in kilojoules per mole. Now the reason why we've actually done this way around is because you can see here that I can cancel out that kilojoule and that kilojoule, and we have mole to the -1 here. If we bring that up onto the top line, that'll convert it into moles. So this calculation here is purely to calculate the number of moles of carbon dioxide that is produced by photosynthesis alone. So what we need to do is we need to put that in our calculator, obviously. There's no way I can do that one in my head. 3.4 times by 10 to the 18. And we're going to multiply that by 6. That's going to get us that. We're going to divide that by 2879. I'm not even pressing the right buttons here. That should get us 7.09 times by 10 to the 15. And that's moles. That's the number of moles of carbon dioxide that worked out, without using the units there. And then all we have to do is then work out the mass. So this is pretty much straightforward. The mass is basically the number of moles times by the MR of carbon dioxide. So the MR of carbon dioxide is 44. I'm going to multiply that by 7.09 times by 10 to the 15, which is in moles. And then if we put that in there, we should get our final answer. So we should have 44 times by 7.09 times by 10 to the 15. And we should get this massive number here. So it's 3.12 times by 10 to the 17. And obviously this is the mass of carbon dioxide that is produced. Okay, so the units for this should be in grams as well, because we're working out grams for the mass. So that's it. So yeah, make sure that you're able to, this is a really tough question, so make sure you be able to work out what the equation was. And the way I worked it out was, you looked at, we needed to work out mass, and to work out the mass of something we needed moles. We were given the kilojoules number here, so I just needed another number and an equation to work this out. You really had to try and work the equation out yourself, so it's a pretty demanding question, this. But there you go, 7 marks. Right, on to the next question. Okay, so this is question 7, and it says standard electrode potentials for 7 redox systems are shown in table 7.1. You may need to use this information in parts A to D of this question. So they've given us a table of loads of electrode potentials and different half equations. Okay, so it says to find the term standard electrode potential, include all standard conditions in your answer. Right, so basically it's the EMF of a half cell. So this is the one that you really just need to try and remember. Compared with a standard hydrogen half cell. Okay, so yeah, basically everything's measured relative to this. Hydrogen half cell having an EMF of 0, so everything's measured relative to that. A little bit like carbon in the periodic table, all the other elements are measured relative to it. Okay, and these standard conditions, there's 3 of them, so I'll put this down here. So standard conditions are a temperature has got to be 298 Kelvin. The concentration has got to be at 1 moles per dm cubed, and the pressure has got to be 100 kilopascals of pressure. So you get 2 marks for this. So you get 1 mark for this bit here, and you get 1 mark for all your standard conditions as well. So basically these numbers are true only at these conditions. So if we have different conditions, and these numbers won't be true, they'll vary. So okay, so the next one. So it says an electrochemical cell can be made based on redox systems 1 and 2. Write down the standard cell potential of this cell. So that's pretty straightforward. It's most positive minus the most negative E0 cell. So we look at the 2 values of 1 and 2. So 1 is minus 2.37 and 2 is 0.34. So it's literally 0.34 minus 2.37. So we'll put that down in there. So it's 0.34 minus 2.37. Bring our calculator back in. So we've got 0.34 minus 2.37. That gives us an answer of 2.71 volts. So it's dead easy. Okay, there you go. And then part C. So it says, using redox systems 3, 4, and 5 only in table 7.1, predict 3 reactions that might be feasible. So write the overall equation for each predicted reaction. Right, so feasible reactions are, we can use something called the anti-clockwise rule, where if we take the most negative E0 value and put that on the top or above the most positive one, and then go anti-clockwise round, and then write the equation as we go, that's the feasible reaction. So what we'll do is we'll start by looking at 3, 4, and 5. So there's 3, and there's 4, and there's 5. So if we start by looking at this, there's 3 and there's 4. Most negative on the top, which is fine. So there you go. There's 3. 3 is most negative anyway. So we can do Al will produce Al3, and the Al will react. So if we go anti-clockwise, we go from here to here, and then if we go back round, so the Al will effectively produce Al3 plus, and the Fe3 plus will produce Fe2 plus. So if we write our equations out, there's our first equation. So we've got Al plus Fe3 plus, and that will produce Al3 plus plus Fe2 plus. Now we have to make sure this is balanced, so we're going to put a 3 in front of there and a 3 in front of there, and that should make it balanced. Okay, so there's 1. Let's say if we take the aluminium one again, because aluminium is this is number 3 here. Aluminium is pretty negative, so we can actually react it with iodine as well. So that again, it's the same one. Al will produce Al3 plus, but the iodine I2 will form I minus. So effectively, the Al will react with the iodine to form I minus, and Al3 plus will be produced. So again, if we write that equation down, so just put Al there. We will need 2 of them eventually, and I'll explain why. And we're going to react that with your I2, and that will produce aluminium 3 plus. Again, it's the same products, apart from we produce I minus here. So now we need to make sure this is balanced. So you've got the 3 plus here. So you see the iodine, we need at least 2 there, but because we've got a 3 plus, we need to actually put 6 here to make sure that balances, a 2 there to make sure that balances, and a 3 there, and that makes sure that we've got enough iodines and aluminiums to make sure it all adds up. Okay, and then the next one, we need to come up with 3 of these, because it did say we need to predict 3. So we could use iron 3 plus, which is this one here. You see this one's positive, and then we've also got I minus as well. So we've got this one here. So again, this one's more negative or less positive. So actually this one would go backwards. So the I minus will produce I2. And then this one would go forward in the normal way, Fe3 plus to Fe2 plus. So the I minus can react with Fe3 plus and will make Fe2 plus and I2 as well. So this anti-clockwise rule makes it a little bit easier to see these. So we'll put that there. So I minus plus, this is going to be Fe3 plus, and that will produce I2 plus Fe2 plus. Again, we need to make sure this is balanced, and you can see we've got 2 there, so we need to stick a 2 there to make sure that's balanced. And because this is effectively given up 2 electrons each, we need to make sure that the charge is balanced, so we need a 2 there, and we need a 2 there as well. Okay, so there's our 3 equations. The anti-clockwise rule is a pretty easy way to work this out. I have got a video that looks into anti-clockwise rules as well. If you look on the playlist to do with electrochemistry or redox reactions, electrode potentials, you'll see how I've used the anti-clockwise rule to work that out. So if you're not sure how to use that method, then it's probably a good idea to check that one out actually, because it is really, really easy to use. So anyway, for the purpose of this, there's 3 marks for all of them. Okay, right, on to the next one. So part 2 says give 2 reasons why it's uncertain. Why it is uncertain whether reactions predicted from E0 values may actually take place. Right, so some of these are very difficult to predict. We can say that they'll work in theory, but in practice they may not. And there is things which might go in the way of that. One of them is the activation energy, and they may have a high activation energy. Okay, so there's one. And the other one is also to do with, remember we talked at the start about standard conditions. They might not be in standard conditions. So, and that's going to have an effect. So remember, all of them reactions are true, the values are true, if we had the standard conditions that we listed at the start. So that was the temperature, the pressure, and the concentrations as well. So there you go, 2 marks anyway. So there are your 2 things. Again, it's like a stock answer really. You know, make sure you know them too. And then D says in aqueous acid, Cl minus aqueous ions react with ClO minus ions to form chlorine gas Cl2, and in aqueous alkali, chlorine gas Cl2 reacts to form Cl minus and ClO minus ions. Explain this difference. Use table 7.1 to help you with your answer. Right. So this is a pretty tricky question. So we are looking at the Cl2 and ClO minus. So we're looking for this one here. There's the Cl2 reaction with the Cl minus, and there's the ClO minus reaction. So this one is most negative. That one there. So I'll put that on there. Most negative. So that's going to be quite useful because when we do our anti-clockwise rule, like I explained before, the most negative goes on the top, and it helps us to work out what's feasible. So you can see here that according to this reaction, under normal conditions, the Cl minus would produce Cl2, and the Cl minus will react with the ClO. And this is because we have the ClO minus and Cl2. This reaction here is more positive than that reaction. So therefore what happens is, because that's more positive, this one here at the bottom, the Cl minus effectively moves backwards. So it moves to the left to allow this reaction to react. Again, if you look at the anti-clockwise rule, it kind of explains it in a little bit more detail on the video. So for the first one, we're going to say that that equation, which is this one here, the bottom one, equation 7, is more positive than equation 6. So I'll put that on there. So I'll put E7, I'll put that in brackets, is more positive than equation 6. So this means equation 6, which we'll put on there, moves to the left, and we're going to say equilibrium just to be specific there. The equilibrium moves to the left. Okay, so there's your first part, and that's under standard conditions. Now, it did say actually in aqueous alkali solutions, the chlorine gas reacts to form Cl- and ClO- ions. So actually, I'm just going to put in there alkali. So in the alkali conditions, and we'll look at them. So actually, what it's suggesting is actually it does the opposite. So if you see here, normally we said before, under normal conditions, that the Cl- ion, that will go left, the equilibrium will shift left, so the Cl- will react with the ClO. What this is suggesting is actually the other way around. In alkali conditions, it turns. And the reason why is because the hydroxide ions will react with the H+ ions in this reaction here. Now, if the OH- reacts with these, it means that equilibrium will actually shift left in this reaction to replace them back again. Now, when a reaction does that, this has an effect on this number here. So when a reaction actually moves left because we've altered the concentration of the H+ ions, this means that this number gets smaller. So what that means now is because this number, obviously, because it said in the question, this number must be now smaller than that number, or in other words, more negative, because of this action that we've taken. So therefore, what happens now is actually the Cl2 now reacts with the Cl2, effectively this reaction effectively now goes backwards, and now we produce, as it says in here, we now produce there chlorine gas reacts to form Cl- and ClO-. It's because now it's going backwards. There you go. So we're forming ClO- because it's going that way. So we just need to explain that in words. So we need to say, we're going to put this into kind of like 3 parts. So the H+ in, and we'll put equation 7, I'll put that in brackets, reacts with the OH- ions, and then we're going to say that equation 7 is now less positive than equation 6. So therefore what we need to say now is that equation 6 moves to the right, and we're talking about the equilibrium. There's the equilibrium is moving to the right, and equation 7, equilibrium, moves left. So that's really difficult. It's a pretty tough thing to try and explain what's happening. Again, the anti-clockwise rule explains that in a little bit more detail, but we've got 4 marks here now. We've got 5 points, and the examiners basically say that you can get maximum for 2 for these ones. So basically, that is just the 2 points that you need, and any 2 from here. So it's best to write the whole lot to make sure that you've explained your answer as fully as possible. So you get 4 marks for that in total. Okay, so on to the next one. So it's in acidic conditions, SN2+ or tin2+ ions react with IO3- ions to produce iodine and tin4+ ions. What is the oxidizing agent in this reaction, and explain your answer. So you can see the SN2+ has gone to SN4, so that's been oxidized. So the oxidizing agent is IO3-. So let's write that down. Okay, so put in there IO3-, and this has this is oxidized SN2 plus to SN4 plus ions. Okay, right. So that gets you the 1 mark just for that one. And then the last one, last part of this question, it's a 50-mark question, so again quite big, says construct an equation for this reaction. So we need to just write down what's actually happening here. So SN2 plus, that's going to react with IO3 minus, which is what we mentioned before. This is in acidic conditions as well, so I'm going to put H plus there. And that's going to produce iodine, because it said iodine. We're also going to produce tin 4 plus, because it said we're producing tin 4 plus as well. And to balance out the protons, we also produce water as well. Okay, because that balances out our acidic conditions. Right, so all we have to do now is just balance it. You can see here we've got the I2 there, so we need a 2 there to make sure that balances. We can see that now we've got 6 oxygens on this side, so we need a 6 there. That's nudged the hydrogens up to 12, so I need a 12 there to make sure that balances. And then it's just a case of balancing the charges now. So I need 5 on that side over there, and then a 5 on that side over there. And hopefully that should all balance. It does, yes. Okay, so in terms of marks, it's 2 marks. You get 1 mark for the actual balancing part, which is 1 there, and you get 1 mark for the full equation for the whole lot. And there we go. There's your 2 marks. So on to the last question. Okay, so this is question 8, and it says dimethylglyoxime, DMGH, can be used to analyze nickel-2 compounds. An excess of a solution of DMGH is added to an acidic solution of a nickel-2 compound. Aqueous ammonia is added, which precipitates out a nickel-2 complex, NiDMG2, as a red solid. A sample of hydrated nickel-2 salt is analyzed using the procedure below. So step 1, 2.5 grams of hydrated nickel-2 salt was dissolved in dilute acid. An excess of an aqueous solution of DMGH is added. Step 2, an excess of aqueous ammonia is added and the mixture is heated. A red precipitate of NiDMG2 forms. An equation for this reaction is shown below. So we've got the equation there, and there's our red precipitate that's been formed. And there's the addition of ammonia. Step 3, the red precipitate is filtered, washed with water, dried, and then weighed. The precipitate of nickel DMG2 has a mass of 2.57 grams. Assume that all Ni2 plus ions have been converted into NiDMG2 solid. That might be useful later on. And it's given us the concentration in grams per mole of nickel DMG2, and this is 288.7 grams per mole. Step 4, a second 2.5 gram sample of hydrated nickel-2 salt is heated in a crucible to remove the water of crystallization. 1.38 grams of the anhydrous salt remains. Okay, so this one says complete the electron configurations of nickel as the element and in the +2 oxidation state. So nickel is the element, so if we bring it over here, they've done the 1s2, 2s2, 2p6. So there's nickel there. So they've done the 1s2, 2s2, 2p6. So then it would be 3s2, 3p6, 3d8, because there's nickel there, it's the 8th element along, and then 4s2 as well. So that would be for nickel. So we'll put that in there. So that'll be 3s2, 3p6, 3d8, 4s2. Okay, and then it says with the +2 oxidation state. So with the +2 oxidation state, what happens is we remove electrons from the 4s orbital first. So because it's 2+, we've only lost 2 electrons. So it's just going to be 3s2, 3p6, 3d8. And the electron has been removed from the 4s orbital. So there's 2 marks available there. So we've got 1 and 2. There you go, 2 marks. Okay. Brilliant. Okay, next one. Okay, so it says the structure of NiDMG2 is shown below. It's a rather large structure. State and explain the role of ammonia in step 2 of this experiment. So if we bring back the sheet again, So we've got there's ammonia, and you can see what it's doing is actually we've gone from DMGH to just DMG. So the H has been removed. We have two of them, so it's removed two protons. So the ammonia is acting as a base in this case. So we'll put on here that acts as a base. And it accepts a proton from the DMGH, because that was the proton that was on the end there. Okay, so that just gets you the 1 mark. And then it says state the coordination number of nickel in NiDMG2. All you have to do is count the number of coordinate bonds, which will be these ones. So it'll be 1, 2, 3, 4. So a coordination number 4. Okay, and so the next one, why does the NiDMG2 complex have no overall charge? The reason why is DMG has a 1 negative charge, and so therefore we have 2 of them that's surrounding there, and therefore it cancels out the Ni2 plus charge. So we'll put that on there. So DMG has a -1 charge, which cancel Ni2 plus charge. Okay, so that gets you the mark as well. And the next one. So it says draw the structure of dimethyl glyoxime, DMGH. So again, it's really easy. You just look at the structure from the top there, and you can see it there, and you can see that wasn't part of it there. So this bit, obviously there was a hydrogen, that's a hydrogen bond. That's the other bit there. So if I kind of draw a circle around that, we literally just need to draw that there with a hydrogen attached to that oxygen there. So let's go for it. So you need a carbon, CH3, double bond nitrogen, and then we have an oxygen and a hydrogen, oxygen and a hydrogen. And there you go, and that gets you that mark. So it looks like. Okay, so on to the next bit. Okay, so this one says determine a possible formula for the hydrated nickel 2 salt. Your answer must show relevant working. Now this is a 7-mark question, so they're after something quite substantial here. It's a big calculation. So we need to work out the possible formula of the hydrated nickel 2 salt. So what we need to do is we need to try and work out the water of crystallization, because we have some water that's attached to it here, and so we need to work that out. So to do that, we need to first work out the number of moles of nickel that we have in total first. So the number of moles of nickel, now we can assume, it did say in the question before, it said that the number of moles, we had to assume that all the Ni2 plus ions have been converted into NiDMG2. So what we can do then is we can then use this value here to work out the number of moles of nickel, which this is the hydrated sample as well. So that's what we're going to do first. So we're going to put at the top there amount of nickel 2 plus, and this is the hydrated sample. Okay, so how we're going to do that is take the mass. Now the mass of this we have the mass, there it is. So the precipitate had a mass of 2.57 grams, and this is the grams per mole as well. And then from that we can work out the number of moles, because we've got grams, that's grams per mole. So we're going to do 2.57. So put that there, 2.57 grams. We're going to divide that by 2.88.7. And this was in grams per mole. Now you can see these two will cancel out, that'll come over there, so that'll tell you you're working out the number of moles. So the number of moles we've got, if we put that into our calculator, should be 2.57 divided by 288.7. And we should get this number 8.9 times by 10 to the minus 3. Okay, and that's moles. Okay, so that's the number of moles of nickel that we've got. Now what we need to do is we need to try and work out the M bit, which is the grams per mole, for our hydrated sample. So I'm going to work it out here. So I'm just going to call that M, and this is in grams per mole. It's a bit like the MR. And so this is of the hydrated sample. Okay, now if we come back to this, it said that we had the second sample here had 2.5 grams of hydrated nickel salt was heated. Now we're going to use this to work out our water of crystallization. So 2.50, and we know the number of moles of the nickel because we have just worked that out. So from that we can then work out the grams per mole of the hydrated sample. So we've got the grams there, we've got the number of moles that we've just worked out. So if we divide them, then we should work out the grams per mole of this sample here that we want to work out. So what we're going to do is the hydrated sample is going to be 2.5. So it's 2.50 grams. That's how much we had that was hydrated. The number of moles we now know to be 8.90 times by 10 to the minus 3, because that's what it said. That's what we just worked out up there. And that should get us 2.50 divided by 8.90 times by 10 to the minus 3. And that should get us a value of 280, as you can see on there, 0.9. And that's in grams per mole. So this is of the hydrated sample. Now this is the one with water in, so we need to work out how many waters make up this mass over here. So we said we had 2.50 grams, and the mass of water in the whole sample it was 250 grams was hydrated, so put 2.50 grams was hydrated, but after we'd actually dried it out, if we come back to this, it said it went down to 1.38 grams. This was anhydrous, so this was after we heated it. So this is going to be minus 1.38 grams. Now if we put that into our calculator, that should be 1.12 grams. And this is the mass of water. And then obviously to work out the water crystallization, we need to work out the moles. We need to work out the moles of water. So moles is mass over MR. So the mass is 1.12 grams divided by the MR. And the MR we said was 18 for water. And so if we put that into our calculator, 1.12 divided by 18. And that should give us 0.062, or in other words, we can put 6.2 times by 10 to the minus 2. Okay, and so this is the number of moles of water in there. Now from that, we can then work out the amount of, or the number of crystals, so the water of crystallization. So that's the next step. Okay, so water crystallization is like a ratio. So we know the number of moles of water, and so we need to divide that by the number of moles of our nickel compound that we had right at the start here. So that will tell us basically the ratio between water molecules to nickel complex, which we worked out before. So this is going to be 6.22 times by 10 to the minus 2. We can divide that by 8.90 times by 10 to the minus 3. And then if we bring our calculator over, put that in there, 6.22 times by 10 to the minus 2, divide that by 8.90, times by 10 to the minus 3. And that's going to give us 6.98, which we can round to 7. So put 7 there. Right, so now we know that actually this nickel complex has 7 H2O attached to it. So what it was asking, if we come back to the original question, is it's asking us to deduce the possible formula for the hydrated nickel 2 salt. Now we know we've got nickel 2 salt with 7 waters of crystallization. So we need to now work out the mass of the kind of anion, because we know the cation is nickel and we know it's got 7 waters. So we need to work out basically what is the mass left behind. So all we have to do is the anion is like the negative bit. So I'm going to put that there. So the mass of anion. Now all we have to do is take the mass of the compound initially. So this is the hydrated sample. There's the mass there. Look, that's the hydrated sample that worked out. So that's going to be 280.9. Now that was of the hydrated sample, so that's everything. And we need to take away the mass of nickel. So the mass of nickel, could bring our periodic table over, is 58.7, because we know it contains nickel. So we're going to take that away from 58.7, and also we know we've got the mass of water as well. Now we worked out we had 7 lots of water, so that's going to be 7 times 18. And then if we put that into our calculator, so let's do that. So let's do 280.9. That was the mass of the hydrated, minus, let's take away the mass of the nickel that we already know, which is 58.7. Okay, and then we also need to take away the mass of 7 molecules of water, and that should leave us with a mass of 96.2. Oh, an MR, sorry, of 96.2, and this is grams per mole. Okay, and so now what we have to do is think, right, we need a formula that could mix in there, so a potential formula. So I'm going to do this bit up here. So I'm going to put formula. So we need to think of something with a mass of 96.2 or roughly thereabouts, and that could easily be a sulfate. An SO4 2 minus, that would have a mass of 96.2. So in terms of the formula, our formula would be Ni SO4 dot 7H2O. And there we have it. There's our formula there. So in terms of the marks that we need to award to this, so we will check this through. So the marks are going to be 1 mark for this is a 7-mark question, so the whole thing's 7 marks. So you would get 1 mark for this bit, so you get 1 mark for that. You get 1 mark for working out the MR of your hydrated salt. You get 1 mark for working out the mass, so there's 3 so far. You get 1 mark for working out the number of moles, there's 4. You also get 1 mark for working out the crystallization. That's 5. You get 1 mark for working out the unknown, which is this one, that's 6, and then 7 for the actual formula right at the end there. So there's the last ones there. So there you go, a big question, it's massive. All we have to do really with that was to work out the crystallization. We're working out the masses of everything, so the mass of your nickel, the mass of your water, and then eventually subtract all their masses away. What mass have you got left? 96.2 grams, which is just sulfate. But that's the end of the paper. Bye bye.